Okay. Let's continue with our first serious example. It's it's called the Sobolev space. There are many Sobolev spaces. Indeed, we will study at least 2, maybe 3 Sobolev spaces to understand what happens if we change the condition in the definition of a space and its consequences on the kernel and the formulas we obtain. So I commence with the Sobolev spaces version 1. To do this, I need to recall a definition again from analysis. Maybe in the second or third course of analysis, you see this. What is an absolutely continuous function? In particular, we stay on 0, 1 with value on R. We can see that the real case, the complex case is similar. This is just to avoid putting bar all the time. We know the definition of continuous function. Absolutely continuous is more, is really a heavier restriction on the function. One way to define it is this way. F is absolutely continuous on 0 and 1 if there is an integrable function G on 0, 1. And let me emphasize what does integrable means. Integrable means that integral from 0 to 1, absolute value of G of t, d of t is less than infinity. That's the meaning of being integrable, such that f of x is equal to f of 0 plus integral from 0 to x g of t dt. That's one definition of being absolutely continuous. Let's see what is the consequence of this. Assume that you have n interval on 0, 1. So here is 0, 1. One interval here, another one there, a little one there. x1, y1, x2, y2. And so assume that 0 less than or equal to x1 less than y1, and then y1. And then you have x2 less than y2. And you continue up to the nth one. This interval are in 0, 1 with a restriction on this. So assume that this is true. We say assume that epsilon is given. Then there is delta such that if the sum of the lengths, not just one of them, y1 minus x1, y2 minus x2 up to yn minus x2, the sum is less than delta if the sum of yj minus xj less than delta. Then you can conclude that the sum j from 1 up to n, absolute value f of yj minus f of xj is less than epsilon. You see, it's way more than continuity. In the continuity, we don't have sum here. We have just one interval. If the distance between y and x is less than delta, then the distance between f of y and f of x is less than epsilon. But here, it can be a collection of intervals, and there is no restriction on the number of these subintervals. And this is an easy exercise to prove. It comes from a measure theory indeed, because when you look at the sum j from 1 up to n, f of yj minus f of xj, look at this formula. If you put yj and xj instead of x, you see this is sum, absolute value, integral from xj up to yj of g of t dt. This is precisely equal to this. These are equal for each j, thanks to this identity. And now you use triangle inequality is less than or equal to the sum j from 1 to n, integral from xj to yj, absolute value of gt dt. And you can write this as sum j from 1 to n, integral over the interval xj, yj, the same function. And since these are not overlapping, it's integral over the union. In other words, you calculate the area under absolute value of G over these intervals here, 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 and here. The absolute continuity here means that if this set is small, then the area is small. And it's not just for interval. In the general setting, even we say something more. We say that if we have a set in 0, 1, of course, measurable set, such that its length is less than delta. Length here means the Lebesgue measure. Then integral over E of gt dt is less than epsilon. That's a generalization of what we have here. So this is the easy part of the definition of absolutely continuity. We can live with that. What is more difficult, and it's indeed one of the deep theorems that we prove in analysis 2 or 3, is that if this is true, then we obtain such a representation. In other words, they are equivalent. So theorem is like this. Suppose that for each epsilon bigger than 0, there is a delta bigger than 0, such that if the sum of yj minus xj, j from 1 to n is less than delta, then the sum of f of yj minus f of xj absolute value is less than epsilon. This is our assumption. Then there is, so it's an existence theorem, G on 0, 1, integrable such that the representation works f of x equal to f of 0 plus integral from 0 to x gt dt. That's a deep result. It's not trivial. It takes some time to prove it. The previous one, this observation, even though you need to know some techniques from measure theory to prove this, but it's not something which is very profound, very deep. However, the proof of this theorem in the reverse order is something profound. For us, we don't care. I mean, we use both of them because they are the same. So that's the definition of absolutely continuity for us. I emphasize the fact that G is in L1 and a theorem of Lebesgue. It's a Lebesgue theorem, one of his famous contributions. Says that if f is absolutely continuous, then f prime, the derivative, the classical derivative, exists, but almost everywhere. This is the terminology he's invented. Or instead of almost everywhere, I say for almost all x in 0, 1 and f prime of x equal to g of x. Again, almost everywhere. So we know what g is the derivative of this. So this representation formula here can be written as follows: f of x is equal to f of 0 plus integral from 0 to 1, so 0 to x prime of t dt. So based on this observation, we can rewrite the definition of absolutely continuity as follows. So in a sense, this is the third equivalent definition. F from 0 to 1 in R is absolutely continuous if 1, f prime of x exists almost everywhere. 2, f prime is in L1 of 0, 1. L1 is the same as saying integrable. And third, the representation, which is in rectangle here. And third, f of x is equal to f of 0 plus. We have to have all three properties. In this case, our function is called an absolutely continuous function. To emphasize that all three are needed, and absolute continuity is something really strong, is much more than being continuous. It's better to go and look for Devil's staircase function in the literature. Look for Devil's staircase function. This is a function which is defined on the contour set on 0, 1. Sometimes it's even called contour staircase function, or contour Lebesgue function. It's an increasing function like this. It here is 0, 1. In the intervals that we exclude, you remember the construction of contour set. The first step will remove the interval 1/3, 2/3. The function is defined to be a constant here. What is the value? You will see. And then we do this because in this step we remove this interval. In the second step, we remove 2 intervals. This one here and this one there, right in the middle. And the function is properly defined such that naively speaking, it's like this here and like that over there. And we continue this construction. So it has infinitely many steps. That is why it's called a staircase function. And at the beginning, it's equal to 0. Finally, at the end is equal to 1. And this height are adjusted such that the function is really increasing, or if you want to say non-decreasing, well, go ahead with non-decreasing. I don't mind to call it non-decreasing or increasing function. Because of these steps on the interval which we remove, 1/3, 2/3, here is the interval 1/9, 2/9, 3/9, and here is 6/9, here is 7/9, and 8/9. That's the second step. Because of all these blue intervals that we remove, f prime of x exists and is equal to 0 on the union of these blue intervals. When you calculate the measure of the blue intervals, it's equal to 1. That is why I can say almost everywhere on 0, 1. This doesn't matter how we adjust these heights. If they are constant on the blue intervals, then f prime is equal to 0 almost everywhere. But we can adjust the height such that it's a continuous function. It's a continuous function. And so you see that for this function, integral from 0 to 1, f prime of t dt is equal to 0, and it's not equal to f of 1 minus f of 0, which is 1. So it's not an absolutely continuous function. Absolutely continuous function should satisfy this property for every x. It doesn't work for x equal to 1. So go and study the details of this Devil's function. It's very interesting. What we need here for our definition, I emphasized here that f prime is in L1. So I write it again here. For absolutely continuous, f prime is in L1 of 0, 1. L2 of 0, 1 is a subset, and it's a proper subset of L1 of 0, 1. Why? Because if G is L2, then integral of absolute value of G of t dt from 0 to 1, I apply the Cauchy-Schwarz inequality with one of my functions to be 1, the other to be G. So by Cauchy-Schwarz is less than or equal to integral from 0 to 1, 1 squared dt a half, and then integral from 0 to 1 mod g squared dt a half, which, I mean, this is equal to 1, and the other one is known too. So briefly speaking, I showed that the norm of G in L1 of 0, 1 is less than or equal to the norm of G in L2, 0, 1. This shows the inclusion. So if the L2 norm of something is bounded, so if norm in L2 is bounded, certainly norm in L1 is bounded too. But the reverse is not true, and I leave it to you as an exercise. It's not difficult, it's really simple indeed. If you work with 1 over x for 1 over root of x, you obtain the functions which is in one of these spaces, but not the other. So the inclusion is really proper. Now I'm ready to define my Sobolev space. L, H is the following set. The set of all functions f from 0, 1 to R, such that, well, 1, f is absolutely continuous. Though f prime, I put more restriction on it, is in L2, not just in L1, a bit more is in L2. And I add some boundary condition. I fix f of 0 and f of 1. So at both extremities, f of 0 is equal to 0, f of 1 is equal to 1. And I want to show my goal. Still, the inner product is not defined, but I can tell you what is my final goal. I want to show that H is an RKHS, and also find its K, find its kernel. That's you will see it's a kind of difficult task. Well, I said RKHS, Hilbert space. Look, we can add these functions, we can multiply by scalars. It's easy to see that it's a vector space. But what is the inner product if you want to have a Hilbert space? Here, the inner product I define. So definition, I define the inner product of f and g in H to be integral from 0 to 1 f prime t g prime t dt. I don't need bar because I work in the real case. Well, I need to prove that it's a genuine inner product, and also it's the norm is complete. Several properties of inner product are easy to verify. For example, linearity with respect to first and second argument, that the scalar multiplication can come out. For example, it's easy to see f plus g and h. That's elementary. Or alpha times f and g is equal to alpha times f and g. That's also elementary. Trivial f times g is the same as g times f, still elementary. And also inner product of f and f is positive because it's the norm of a function squared. What needs a bit of attention is that why, if f inner product with f is 0, f is identically 0? Why? Back to the definition, it's f prime. Attention, f prime is not continuous. That's a delicate point. I explain. F times f is integral from 0 to 1.
Yeah, but by the boundary condition, f is continuous.
Yes, absolutely. But you need to be careful here precisely. When this is equal to 0, integral from 0 to 1, f prime squared dt equal to 0. What is the conclusion?
F prime is 0 almost everywhere.
Please stop here. Very good answer. F prime of t equal to 0 almost everywhere. And why from here we can conclude that f is equal to 0? Where is this representation?
Fx was equal to f0 plus the integral of f prime.
Exactly. We have this one. F of x is equal to f of 0 plus integral from 0 to x f prime dt. That's an important property of absolutely continuous function. So f of x equal to f of 0 plus integral from 0 to x f prime t dt. As you said, this is 0, and you also mentioned this is also 0 boundary value. So we have f of x 0 for all x. In other words, f identically is equal to 0. So it's a good inner product. It satisfies all the properties.
Just a question.
Sure.
Is, because f prime is equal to 0, we can say that the f is constant almost everywhere also.
No, I just gave you, I just raised your attention here. For absolutely continuous function, yes, but if not, here it is, devil's staircase. This is a function for which f prime is 0 almost everywhere, but it's not a constant function. It's an increasing function from 0 to 1.
Okay, thanks.
For us, 100 years, 120 years after, it's easy to, read this and understand. But imagine 100 years ago when Lebesgue and Cantor and others thought about this thing. It wasn't easy at the time. I fully understand why you say, and I have the same feeling too, when f prime is 0, f has to be constant. No. Thanks to the work of great masters. You see a function which is increasing, 0 almost everywhere, but not constant. But in our case, we consider a subclass absolutely continuous function for which what you say is correct. If you want to correctly state what you say, you can put it that way. If f is absolutely continuous and f prime is 0 almost everywhere, then f is constant. That is true. Okay, so we have...
I ask another question about this discussion?
Please.
Can we say that f prime is 0 absolutely everywhere, then f is constant absolutely everywhere, almost everywhere, sorry. F prime is 0 almost everywhere, f is constant almost everywhere. Can we say this?
Be careful about what you mean by f constant everywhere. Maybe you mean that f is like this, but the constants could be different. Because f is constant here, f is constant here, is constant here, but not the same constant.
Yeah.
So,
Okay.
yeah, it depends what you want to say.
Yes.
If you want to say that f is constant, just one constant, almost everywhere, then no. Still, if you want to say that f is constant but different constants, you need to be careful. You need to be careful. We have constructions which is way more complicated than this. And still f prime is equal to 0. And we do not have intervals on which f is constant. So it's a very delicate subject in measure theory. To keep ourselves from error, let me write the theorem because we can use it. If f is absolutely continuous and f prime equal to 0 almost everywhere, then f is constant. The way we understand constant everywhere. Other than that it means if you remove the absolute continuity, we have many bizarre behaviors. You need to be careful. Okay. And what remains? Completeness. Completeness is almost for free. And that's a gift from Lebesgue. As I mentioned earlier, one of the greatest achievements of Lebesgue was to define LP spaces, and they are complete. What does this mean? This means that if you have a Cauchy sequence in LP, if Gn is Cauchy in LP, then there is, and this is the essence, the existence, there is G in LP such that Gn goes to G in LP nor. That's the important message of Lebesgue. And now let's go back and see what Cauchy means in our setting. Let Fn be Cauchy in H. So for this, recall what is the norm of f in H. The norm of f in H is integral from 0 to 1, f times f, which is f prime of t squared dt root square. That's the same formula we have here. Same formula we have here. I took f equal to g. And I can write this as the norm of f prime in L2 of 0, 1, L2. So Fn Cauchy means that given every epsilon, there exists an n such that if m and n are big, then norm of Fn minus Fm in the space H is small. But what is Fn minus Fm? Is Fn prime minus Fm prime in L2 by this identity. Therefore, this means that Fn prime is Cauchy in L2 of 0, 1. L2 complete, there exists G such that Fn prime goes to G in L2. We already had an inequality. Norm 1 is less than or equal to norm 2. Here it is. Norm 1 is less than or equal to norm 2. So if something converges to 0 in L2, it also converges in L1. Therefore, we have this strong convergence also. Fn prime goes to G in L1. I need both. What are the consequences of these two? First, look at the representation for Fn. Since Fn is in H, we have the representation Fn of x is equal to Fn, but Fn of 0 is equal to 0. So I remove this. Integral from 0 to 1, Fn of Fn prime of t dt, and here is x. I made a mistake. We know that this goes to integral from 0 to 1 g of t dt, because the convergence is also in L1. Again, I wrote 1. We know that the right side is convergent. Therefore, I come and define function f by the formula 0 to x gt dt. That's my definition. By definition, f is absolutely continuous. The observation here, indeed this one, since f prime is equal to g almost everywhere, Fn prime goes to f prime in L2. That's what we have here, which is the same as going saying that Fn goes to f in H. Before this, I have to verify two things. Indeed, it has to come before this, but they are rather elementary. By definition, f of 0 is equal to 0, just to make sure that we are really in H. And also, why f of 1 is equal to 1? Because f of 1 is equal to integral from 0 to 1 g of t dt. There is no indication that this to be 0, but if you go back again and look at this, Fn prime goes to G in L1. So here I can write lim n times infinity integral from 0, 1 Fn prime t dt. because Fn prime goes to G in L1. And now I know that this is equal to Fn of 1 minus Fn of 0, and both are 0. So f of 1 is also 0. So this makes sure that f is in H. This should come before this and this one after, but it's okay. We have Fn in H converges to f in H, therefore H is a Hilbert space. More than that, not just Hilbert space. Evaluation is continuous. Again, back to the formula, f of x is equal to integral from 0, 1, f prime t dt, 0 to x. Taking the absolute value, we have less than or equal to 0, 0x. This one. And then Cauchy-Schwarz again, with one function to be 1, the other to be absolute value of f prime. So Cauchy-Schwarz is less than 0 to x 1 squared dt root square, integral 0 to x f prime t squared dt a half. Less than or equal, this is root x. And here, be a bit generous. That's not a mistake this time. I replace x by 1. And this is root x norm of f in H. So absolute value of f of x is less than or equal to root x fh. I can also write this as evaluation at point x of f is less than is, so it's continuous, and so ex is continuous, and norm of ex as an element of H to R is bounded by root x. You see, that's one estimation. So by now we have an RKHS. Good. Is this optimal? Is this really an upper bound for the norm? I very quickly convince you that this is not the optimal answer, because I started with this definition, with this one, with this representation, because this is f of x, but the integral on the right side is f of x minus f of 0. F of 0 is 0, so we obtain it. We also have what is integral from x to 1 f prime of t dt. I mean, absolutely continuous. So this is f of 1 minus f of x. F of 1 is 0, so it's minus f of x. I can write f of x is equal to minus this. That's another formula. That's another formula for f. And if I do the same calculation I did here, I mean, take absolute value inside, then apply Cauchy-Schwarz. What do I obtain here instead of root x? You see that? If I do the same calculation,
Square root of 1 minus x.
exactly. Same calculation gives me this. And therefore, also norm of x will be less than root of 1 minus x. So at least I have two, one here, less than root x, another one here, less than root of 1 minus x. And none of them is indeed optimal. Root of x is not good. Root of 1 minus x is not good neither. So the question is this. What's the norm of Ex? That's the question I will answer next week. To show you what I will use, I go back to the second part. Here it is. Here is the formula I will use to obtain the norm of the evaluation functional. But before using this formula, I have a long road to traverse. I mean, I have to find K, I have to find the kernel. Here, I know that it's a reproducing kernel Hilbert space, but still I do not have the kernel. I have to find the kernel and then use the kernel to evaluate this. So more honestly, this is my second question, and question 1 is what's K? This is what we will do next week. We will find K, and we will see. For that, we need techniques from distribution theory and ordinary differential equations. It's not an easy task, but at the end of the day, we will succeed. We will obtain the kernel K, and then we will use the kernel to obtain the norm of K. So the answer is available in the book I presented at the very beginning. You can go and read it in the book. My suggestion is to try to do it yourself. And I assure you it will pay off. You will see what are your difficulties and possibly why you do not succeed. And then you will be able to discuss and overcome all the difficulties one by one. Well, that's enough for today. Thank you very much, all of you. And well, hope to see you next week. I'm available if you have any question.